Thank you. Can you hear me? So thank you, Marta. I want to first begin by making a pitch. I was talking to Stephen and Marta before. There is an American Physical Society if you're a student and you want to be involved in physics meetings. And there's local meetings called the Four Corners. And the next meeting is going to be in October at the University of Denver. So if you want to put something on your resume that says you've given a talk, or you want to see what else is going on in the region, it's a great opportunity. So, and for a student, it's absolutely free to join. Okay, so I'm going to talk about the meaning of mass, and it's not GMM over R for a potential, or R squared for a force. I want to first tell you a little bit about what is particle physics, what do we do. The goal is to try to identify the smallest bits of matter, fundamental particles, things that have no physical extent. And if you want to wrap your mind around something that's sort of hard to grasp, is an electron. Electron, so far as we know, has no physical extent. It's a point-like object, an indivisible part of space. But yet it has properties. So then we want to understand how these objects interact with each other. And those are the fundamental forces. And these two together, we've now put together in something that's called the standard model of physics. And this is the picture here of the standard model. They're quarks. These are fundamental objects. And quarks, just these up and down here, this is plus 2/3 fractional charge minus 1/3. With just these two, we can make up everything in our world. We can make up protons, neutrons, and we now have identified in the lab 6. They come in doublets like this. No one knows why yet. That's an open mystery. And this 3 family for quarks, all of which, so far as we know, are point-like the electron. So we think they're fundamental. There are also things called leptons that, like the electron, there's a muon, and there's a higher mass family called the tau family. And along with those, there are 3 neutrinos. There's an electron neutrino, a muon neutrino, and a tau neutrino. As you move across this way, you go up in mass. And some of these quarks are fundamental, but the top quark, for instance, is 175 GeV energy. That's mc squared. So 175 times more massive than the proton. The fundamental forces, there are 4. There's gravity. Oh, sorry. There's gravity that is important for big objects, long distances. We know lots about it on the Earth. It's one of the big mysteries at long distances. And I think this is going to be pretty interesting in trying to identify what dark matter is, dark energy is down the road, trying to understand what gravity looks like on long distance. There's electricity and magnetism, which you're all familiar with. There's the strong nuclear force that binds these quarks together, which is why we don't see them in everyday life. We have to make them in collisions. And then there's the weak force. And this orange arrow between the two, we found that these two together, electricity and magnetism and the weak nuclear force, are similar. They're called the electroweak. And it's these two together that, and trying to explain why they show up differently in the lab, is what gives rise to the Higgs field, or the Higgs force. So it was this mystery, why these are 2 different forces explaining different physical phenomena, and yet what we observe is something very similar between those 2. So I'm going to go through this quickly, but basically this unified electroweak theory, putting together electricity and magnetism and the weak nuclear force, came about because at very short distances the strength of the interaction is the same. At 10 to the minus 18th meter, so that's pretty small. You know, human hair is 25 microns. So this is down 12 orders of magnitude. But when you go just 30 times this distance, it turns out that the weak interaction is down by 10,000 from electricity and magnetism. And sort of because they have equal strengths, they concluded that, theorists concluded that they were essentially the same force, and something had to cause this difference in terms of unifying the weak nuclear force and electricity and magnetism. The difference between these observed strengths as you move away from the objects was due to what carries the force. So for electricity and magnetism, it's the photon. We don't believe in action at a distance. At least I don't. You know, something travels from one object to another. From the moon to the Earth, we believe there's a bath of gravitons. We haven't found it yet, but that's what we believe. And that's what we find when we have an electron or a charged object with an electron here, a charged object with an electron here. They repulse. And they repulse because they see the impact of the photons coming from the other charge. In the weak nuclear force, the carriers are these W and Z bosons. And there can be a mixing between these two, between the Z, which is neutral, and the photon. Ask me questions, because I'm used to this terminology and you're not. So the standard model of physics that currently exists has been around for at least 20 years. These are the quarks, these are the leptons, and these are the force carriers. That's all there is. And all of these objects have been detected by physicists, even the neutrinos. There's a number of neutrino experiments going on now. The closest are in South Dakota at the Homestake mine. But all of these quarks and leptons have been found. So again, I want to talk about these force carriers. So the photon is the electricity and magnetism force carrier. The Z and the W, this is a charged object. It's called the W boson, Z boson. These all have unit spin or zero spin. These are all fractionally have half integer spin. But the Z and the photon can interact. And the G stands for gluon. That's the force carrier for the strong nuclear force. Okay, so I want to say a little bit more about electroweak theory. And I'll just mention a couple highlights. One is the electroweak theory predicted ahead of time the ratio of the W and Z mass, the force carriers for the weak force. It explained the ratio of coupling between electricity and electromagnetism that was seen at this very short distance. And it explained sort of a technical fact, but when the Z particle, the carrier of the weak nuclear force, decays, it decays to electrons and quarks. And it told how they spun. They tend to spin either right-handed or left-handed, but it explained that phenomena. So it turns out that there was a huge theory initiative that started in the 80s, went on for a while sort of saying, okay, you could measure this in the lab, and they wanted to test things to 1%. It was so important for the fundamental theory that there was a huge number of people employed to do this, mainly at Stanford. So at high energy, it turns out this electroweak theory had problems with divergences. You could imagine scattering Z bosons on Z bosons, and it turned out the calculation showed that this should diverge. It should be infinite. So we knew there was something else that had to be there. So the fix was something called the new field. So I mentioned 4, right? Electroweak, gravity, electricity, and magnetism, strong. So the idea was to introduce a new field called the Higgs field. So imagine this is a field that pervades all space. It doesn't have a direction like from positive charge to negative charge like electricity and magnetism, but it's a field. And if the field exists, then the known particles would interact with that field. And it would fix these, what happens with scattering cross sections at very high energies. Basically made them finite. So introducing this Higgs field changed the results of scattering cross sections, but it took a long time to measure those. The first idea for this came from the 60s, and Peter Higgs, and the Higgs boson bears his name, but there were 5 other people in 3 groups that had a similar idea. He was actually the first person to say, okay, if there's a field, then you have to have a force carrier of the field, and that would be the Higgs boson. He was the first to say that, and it turns out it's interesting now because they think there'll be a Nobel Prize awarded for this idea. And so they're all saying, well, I submitted a paper a month before, but it was rejected, and then I resubmitted it. Okay, so these are all the objects shown pictorially. The only thing missing now is the Higgs boson, you know, in the standard model up here, and we think it's pretty massive. And these were these theory initiatives that I was telling you about, where people said, okay, you can make these measurements, and you should get this result. So these are shown as 0, 1, 2 standard deviation from what's expected, and sort of the 1% level. So these are, just think of these as a bunch of different measurements. And they were all agreeing to within 1% if you had a Higgs particle up here. So we've known it's been there, or should be there, or something like it for a long time, but it hadn't been found. So now where does the mechanism for mass come from? So the Higgs field interacts with all particles, and it affects the space that particles travel in. And it's what gives them mass. So imagine as you drag an object through the field, the stronger the drag, the bigger mass you would have. The less drag, the less mass you would have. Things that have more mass have a bigger interaction with the Higgs field. That's the way to think about it. So it turns out not only do these weak force carriers, the W and Z, they pick up a mass. They're heavy. They interact with this field. Even the neutrinos, they can travel right through the Earth. There are lots of experiments studying how the neutrinos interact with matter at different angles as the Earth spins and they're coming from the sun to experiments. So we say that the Higgs boson, if you can find it, it's really the field, but the Higgs boson is the origin of mass. That's the idea. And you might ask, where does the Higgs boson get its mass? And the idea there is the Higgs boson interacts with itself. There's a self-coupling in the field that gives the Higgs mass. So even though, and I want to back up because I've been asked this question before, when you think about the proton and the neutron, most of their mass doesn't come from interaction with the Higgs. It comes from kinetic energy. The quarks are bound inside, if you want to think of these bags of protons and neutrons, they're going around very fast. So most of the mass is kinetic energy in protons and neutrons. But the individual quarks, the up and down quarks, get their mass from the Higgs field. Okay, so I put this on because I think it's sort of cute. I was asked by this, why do physicists call this the guard particle? Well, we don't. But it turns out Leon Lederman, who won a Nobel Prize for discovering the mu neutrino, wrote a book. And he didn't think it would sell, or his publisher didn't think it would sell unless it had a good name. And so Leon wanted to call it the goddamn particle. But that wasn't allowed, so they called it the God particle. So the media loves it, and they keep saying, well, have you found the God particle yet? So this is the way to think about it. You have quarks, forces, and you have the Higgs field underneath, underlying everything. And that's probably what I want you to remember from this talk. Okay, so in the simplest version of the Higgs mechanism or Higgs field, there's just one particle. It's called the Higgs boson. It's the force carrier for the Higgs field. because people have been searching for a long time, there are lots of extensions to the simplest theory, and they have multiple particles. There can be charged Higgs, there can be neutral Higgs. There are lots of extensions, and keep this in mind at the very end, because I'll tell you up front that we have not claimed as an experiment that we have observed the Higgs boson. We've claimed that we found a particle, but we need to do more measurements before we claim it as the Higgs particle that's there in theory. Okay, so from these two curves, I want to show you from all those precise measurements that I showed you, where they were all good to 1%, this sort of showed us a probability curve, if you like, versus the mass of where the Higgs would be. What would be the best fit for it? The best fit was for 94 plus 29 minus 24 GeV. So we knew that it was in here, or there was going to be something bad happening with theory. We'd have to alter the standard theory. And what happened right before we found something in early 2012 was that there had been measurements of measuring the mass of one of the quarks. And we took the heaviest one, which was the top quark, versus one of these force carriers, the W boson. So this is the mass of W boson versus the top mass. So you have two things that drag through space, drag through the field. And so there could be different lines where the Higgs might exist. And our great accomplishment was that the main story until we actually found something was we'd ruled out 450 GeV of space. So it could possibly lie in this narrow band here, 115 to 127. Or it had to be very heavy, from 600 up to 1,000. And even beyond that, we had ruled out some of that space too. So we knew that it was bracketed either with what we'd call light Higgs or a heavy Higgs. Okay, so why do we have to do this in an accelerator? Well, the Higgs field is everywhere. So why can't we find the boson in our labs? And the problem is that there's just far too little energy to excite the field to make a Higgs particle in the lab. You remember E equals mc squared, and we're talking about 125 billion electron volts of energy. So we need a lot of energy in a small space, and the only way we know how to do that and detect the objects is in an accelerator. Still, the cosmic rays that hit the upper atmosphere are higher energy than what we could make in the lab. But the way we know to do it is take two particles, give them as much energy as we can get, smash them together, and then look for physical object. So, as I mentioned, the theorists had this idea in the 60s. There was a huge theory initiative in the 80s to precisely measure everything. And so the search has been on by experiments for a while. It's just that, as I say here, we looked and looked and looked, and we didn't find anything. There was no sign of the Higgs boson. There was even a special accelerator built with electron positrons that would annihilate on each other up to 115 GeV, looking for the Higgs. And they didn't find anything. So, you know, being a particle accelerator, we always need a better accelerator, right? We need a more energetic and more intense accelerator. So let me tell you about the particle accelerator. And for people who heard me talk 2 years ago, some of these slides you might have seen before. But the place where this research is done is just outside of Geneva, Illinois. Marta gave me some Geneva cookies right before. It's called the Large Hadron Collider. All of the objects that are composed of quarks are called hadrons. That's why it's called the Large Hadron Collider. And the machine was designed to run 7 trillion electron volts, protons colliding with 7 TeV protons going the other way. For now, we've only got to 4 TeV on 4 TeV. The accelerator currently just went down last week, and it will be down for 2 years. to upgrade the accelerator to get to 7 TeV on 7 TeV. It's a technical issue, but there was a superconducting problem that needs to be fixed in terms of splices between magnets. So it's a multi-stage accelerator. The beam gets ejected into this large ring in opposite directions at 450 GeV, and then once you go around, you apply an RF field, electrical field, boost it a little bit faster, you ramp all the magnets up, and you keep doing that. And it goes around about 80,000 times a second. The beam is small. It's like a soda straw. So you have soda straws interacting on soda straws. And there are places where we can squeeze it down to sort of 100 microns.
How does that straw compare to the diameter of the actual ring there?
I'll show you a picture. Soda straw is insignificant. So here's the picture of the ring. You can see the Alps in the back. It's 17 miles around. You know, if you're thinking about the size of a soda straw. It's located 100 to 500 feet underground. There's 1,200 pole moments. They're each 15 meters long. The big magnets. And there are almost 400 quadrupoles. These are focusing magnets. Dipoles bending in one direction, if you remember the Lorentz force. The bores are interesting. So if you have positive particles going in both directions, you have positive particles hitting positive particles. So you have to have two different magnetic fields that cause the protons to bend in the same direction going around. Okay, so what I wanted to say is this is Lake Geneva here. These are the Alps. I have another picture, I think, right after this that is closer view. You can see that there's several accelerators in here. This is where they start. They put it in this ring. Some inject that way, some inject that way. There's an airport here. And it's completely different than in the US in that people are happy with beams and tunnels going under their house. That would never happen in the US. Okay. So what happens is this is looking in the tunnel. The protons are accelerated almost up to the speed of light. Actually, it's 4,000 times. Their energy at 4 TeV is roughly 4,000 times more energy than they have at the rest mass. And the magnets that have to bend the protons basically run at the state of technology. It's 8.36 Tesla. 5×10 to the -4 is the Earth's magnetic field. Tesla, so it's pretty wimpy. There are 4 places around the ring where collisions occur. 2 are in 2 big experiments. This is a picture of the dipole magnets that are 15 meters long. You can see they're sort of complicated because they're run at liquid helium temperatures in order to make the niobium-tin superconducting. Otherwise, it would be too much to pay for the research. And so there are different utilities at the end that create vacuums. There's a liquid nitrogen port. There's a liquid helium port. And right in the center, there's 2 bores where the protons go one way, the protons go the other way. Here's another picture with someone riding by the magnets. I put this up because I think it's kind of interesting. You know, black body radiation is 2.7 degrees above absolute zero. We're running at 1.9 degrees above absolute zero. Although I have colleagues, I met someone that does atomic physics. They claim they have the coldest temperatures in the universe, and that's just no, nano Kelvin. Yeah. But what I wanted to show you is there's actually a person welding down here. Can you see that? Oh, yeah. And it turns out there's so many of these connections that it turns out on some of the magnets there's a slight splicing problem. And when something goes from superconducting to normal, when they warm up for some reason that you didn't want it to, like a magnet fails or a power supply fails, you have to dump a lot of energy quickly. And in 2010, there was a failure, and it turned out the tunnel filled with helium gas and just froze. It froze all the moisture out of the air, so you had to wait and heat it up. So the reason we're going down now is actually to look at all the splices, and so we can go to higher energy. Okay, and I want to say that this is a large enough facility, 17 miles around, that we see the effect of the Earth's tides on land. So what you see here across the bottom is time in days, like -4, -2, -3, -2, 1, 0. Sorry, we're physicists. So, and what you see are 2 high tides each day. And this is very precise. It's just in the orbits. We can see the ring breathing in and out over the day. And so we have to adjust the orbits for the Earth's tides. Okay, so the experiment I work on is called CMS. CMS, the C stands for compact, but you might not think it's too compact. This is the tunnel shaft that goes to the surface. And everything that we built had to go either down this hole, in terms of these big yellow cranes that you see on the outside, or there is a freight elevator, but it turns out that our magnet that we have in the experiment is so strong. It's the largest solenoid in the world, most powerful solenoid, that the extended field is such that it actually impacts the freight elevator. We decided to not spend a lot of money putting steel around the freight elevator. So you don't go down the freight elevator, go down the stairs if you have to go with everything on. Okay, and this shows underneath now. So this is the bottom of the hole, looking from the ground up, 300 feet below looking up. This is the way it was in 2005. We put in the power supplies and racks in 2006. 2007, we started to fill in the detector. These rings here are steel, and the magnetic field goes right down the center. So that it goes in a tube, goes down the center, and the steel is needed for the return yoke on the magnetic field. The magnetic lines come out, and they have to come back through that steel. In 2008, we'd instrumented most of the detector, but we didn't finish until 2009. So this is a picture of the superconducting solenoid. You may have wound wires, same idea, in a lab. So this was designed so that it fit by 1 centimeter on each side down the shaft. And then when it got down to the bottom, it was turned horizontal. And then it was plugged in place. And then we put the steel yokes, the return path for the magnetic field on the outside. And I want to talk about results from 2 experiments. I'm on the CMS experiment. That's the one on the right. Our competitor, it's actually larger in size, is called Atlas. It has more people. It's about 30% of the people on CMS are from the U.S. On the right side, it's about 10% are U.S. people. And they're big collaborations. Just think of it like a company. There's about 2,000 people that work on this. And we have about 2,000 that work on this one. So while it being compact, this one is 15 meters in diameter, length of 21 meters, almost a football field. Football field would be 100 meters, so a fifth of a football field. It has a mass of 14,000 tons because we used all steel. And inside we used a lot of brass. I'll say something about that in a minute. Our competitor has a much bigger experiment. See, it's twice as long and larger diameter, but it's only half the mass. doesn't absorb things as soon as we do. And because these experiments are in Geneva, right next to France, we always use the Eiffel Tower as a comparator. And so CMS is weighs twice as much as the Eiffel Tower. The Atlas experiment's about the same. Okay, so to detect particles, we're going to have these collisions and things are going to come out. And we want to be able to reconstruct everything. We want to be able to collect the photons that come out, the electrons that come out, the muons that come out, hadrons, protons, neutrons, everything. So we want to have a hermetic detector. This is what the experiment looks like. Collisions are here, and the magnetic field goes this way and then comes back around. But from this point out is entirely instrumented. I'm going to sort of walk through quickly with a picture that will show you how we have them instrumented. So here's a slice right through the center. So we have a collision in the center, and these are tracking chambers, and the tracking is all silicon. I think we have 2,300 square meters of silicon that we use to track particles. Beam strikes right in the center, and then we have things coming out.
Straw size scale?
Straw size scale, about like this.
Right.
And we're able to see an interaction to within about 300 microns along there. So they can interact anywhere along there, but we can assign the particles to the right collision from the tracking devices. Basically, anything that curves is charged. So these are electrons that come out and will stop. These are what we call pions or protons, things composed of quarks. They will pass through this first device and lose their energy in something called a Hadron Collider, calorimeter. And then there are things that interact with the weak force, like the muon. It goes all the way through. It changes its curvature because the magnetic field is going into the board here and out of the board here. So the curvature changes. And then if something's neutral, then we'll just see a splot of energy like this, or here would be a neutron leaving energy. So we have pretty good coverage. We don't see neutrinos. It's not a massive enough detector to stop neutrinos. They'll go right through the device. Any questions? It's a quiet audience. Yeah?
So is that silicon, is it like a wafer with,
yeah, they're 300 microns thick, and we typically have 4,000 channels in a centimeter square. They're pixelated. Each pixel is 100 by 150 microns in size, and we can look at from the electric fields that are applied between them, we can look at the energy sharing because they're also in a magnetic field. Here's the solenoid. So all of this is inside.
So you're getting the path by looking at coincidences then?
Right. And coincidence is typically 25 nanoseconds. So we know things to within 25 nanoseconds. And I also wanted to say that for anyone who may have been educated, oh, you had a question?
Yeah, I was more curious about the collisions there. I don't know if the collisions are happening too rapidly, but
they're happening this way.
The energy of the collisions with the amount of energy and mass of the scattering.
So that's a great question. So it turns out protons are made up of a neutron, or let's say an up quark, and a down quark. And we usually draw things in between, but they could go anywhere. These are gluons that bind them together. And it turns out you can have another proton over here with up, up, down. And when these go by and collide, we don't see an annihilation. What we typically see are like up quark, interacting and that creating the strong collision. But the energy carried by the other quarks or gluons just pass through. They go right down the line. In fact, the most likely collision, but it's sort of technical, is from fusion of two gluons. We call it glue-glue fusion. That's most often what we see. We have gluons that interact. Most of the energy goes right down this pipe. And we only see the energy coming from the hard points that come out in it. So that's a great question. More question? Yes?
How often do they annihilate?
So there's no annihilation here. But you might be thinking Fermilab has a facility of protons and antiprotons, and there they really do annihilate. Here they just scatter. And how often does that occur? We have about 10 interactions every 25 nanoseconds. Maybe that's the way I think about it. I can convert it to seconds if you want me to. Okay. What I did want to say is, as the energy goes up, for people who might have a background in nuclear physics, and you think about tracking individual particles, you tend to have now so much coming out that we tend to think of energy flow or particle flow away from an interaction. So mostly what we see are lots of tracks, and neutrals are energies. So we see this energy flow away. This is called jet production. And this is a picture of one interaction with 3 jets coming out. That's what we typically see. We have to reconstruct everything. But the way you think about it, you ask this question. So here could be a quark that's coming out this way. We say it hadronizes. It turns from a bare quark in 10 to the minus 25 seconds into a particle. And then we see the shower coming out. Okay, so this is the detector close to when we closed it up, near the end. Again, you can see someone on a cherry picker here. That thing through the center, sort of limp noodle, is a beryllium beam pipe. You want to have a really low Z material. So when things interact, they can pass right through because our detectors are outside of that. Okay, so silicon. So we have 2,300 square feet of silicon, and these are, every single element is 100 microns by 150 microns. You know, and that's why I said 4,000 channels in a centimeter square. So we sort of have this device that went inside of this device that went there. And then what we worked on at the University of Colorado were these pixel devices. I just mentioned these. It's sort of the eyes of the detector that go right around the beam, get the first look at what's going on. There's 65 million of those. One of our postdocs is in here inserting it. Okay. I just wanted to say that the muon detector, I already mentioned, interact weakly, so they go through everything. We use 12,000 tons of steel to sort of stop everything. So the only thing that goes through is something interacting weakly, a muon. And because we have so many different interactions, triggering on muons is a great thing to do because not many of them get through everything. The device that measured energy from neutrons and protons or pions is called a Hadron Calorimeter. It's a big group, like a company. And we have people from lots of different companies. The Russians participated by providing all the brass. They convinced their government to melt down a number of artillery shells. And then they poured them to form these funny shapes here. They're sort of these noses that would go right on the outside. And they're read out with scintillating fibers. Everything has to be fast. Light is really fast in terms of communicating. So what happens is you lose energy in the center of this plastic, slows down in the steel, leaves energy as it goes through the plastic. The plastic fluoresces, In blue, it's picked up by this green fiber. It's wave shifted and then goes out to a photosensor. And so if you measure the amount of light you get out of each tile, you know how much energy went into that little segment. So here's the detector altogether in 2009. So that's the detector. I mentioned the accelerator. Now the question is, how hard is this going to be? Can we find anything? Is it a needle in a haystack, and can we find the needle? I think it's actually harder than a needle in a haystack. But it turns out there were Fermilab experiments that found that they found something called the top quark that had a cross section. That's the probability for something to happen, if you like. 1 part in 10 billion. So you have to be able to trigger on these objects and not fill up all of your buffers. Remember, you may or may not know that the World Wide Web started at CERN. And it was done to communicate, not by Al Gore, by the way. it was done to communicate internationally with scientists. So they developed the language, HTML, and they're still the leaders in internet and sort of new languages on the internet. But the Large Hadron Collider has 100 times the production capability, which we call luminosity, than at the lab in the US. And the experiments were designed so that we could discover Higgs masses for all masses less than 1 TeV in 1 year of running. And I think that's why I probably made the mistake of telling Marta 2 years ago, oh, well, invite me back in 2 years. We'll have found it by then. So let me tell you how this is produced. And this is a Feynman diagram. But basically, these are gluons coming from one proton, gluons from another proton. And there's something called gluon fusion. So gluons couple to quarks, because they would bind the up and down quarks in a proton. Here they're binding to top quarks like this. So these two gluons carrying a lot of energy, and they make top quarks, and these couple to an H, which is a Higgs. That's the way one might be made. And here's another way, which we call vector boson fusion, where you have a quark comes in instead of a gluon, and the quark can couple to one of these vector bosons, and you can have vector boson from the other side colliding with each other, making a Higgs particle. So we tend to think, because the Higgs particle couples to mass, that you want to make top quarks, the heaviest things you can make, to make a Higgs particle, and then we have to let it decay. So this is how we produce it, and this is how it decays. So it decays by one of the channels. It's pretty rare, but it can decay into 2 photons by, again, coupling to top quarks and then going to photons. So what we're going to look at in the experiment is 2 photons. And we're also going to look at something 4 leptons, like electron, electron, or muon, muon, electron, electron. And this plot shows you the branching ratio. How often does it go into this channels? Most often, the Higgs particle goes into top quarks, or these are tau leptons. Those are hard to see. It can go into bottom bar quarks. Those are also hard to reconstruct. So we wanted to pick the things that are sort of easy to see experimentally but aren't produced too often. So those were 2 photons. Or this is vector boson called the Z with vector boson, another vector boson. These go to leptons, like muons. This is leptons, or it turns out the W boson and a W boson being produced by Higgs can go into 2 leptons. The easiest things for us to trigger on are strong electron, an isolated electron, an isolated muon. Remember I mentioned muon passed all the way through, or an isolated photon. Okay.
Why is the 170 GeV, there a resonance?
There's a threshold at that point that isn't shown here. It's when you hit the, good question. So the W boson is 83 GeV. And at the point you change from making a real W, from a virtual W to a real W. So once you can produce them in the lab, then you have a big peak for right at this dip for W plus, W minus, or for Z boson, Z boson. So that means all the branching ratios take a plummet right when those channels open up. Good question. Okay, so this is what we might see. So if you had a low mass, less than 135 GeV, it's below threshold for producing some of these bosons. And so you would look for 2 photons. This is what you might hope to see. This isn't data. This is simulation. So we would look at all the possible combinations from photons, isolated photons from other physics processes. We put them together and we'd hope to see a peak. And our best at this point would only be a signal to background of 1 to 20. So it isn't very good. You also could look at the same thing into 4 muons. So in this picture it's a little hard to see, but you see these green lines are going outside the detector. This is sort of a golden signature, but it's even rarer than the 2 photons. But we look for that. Okay, so this probably answers your question that you asked about how often they interact. So protons collide 40 million times a second. They generate a megabyte of data each time. So this is 40 terabytes a second, or 40 disk drives per second that we would fill up. But only 1 in trillion of all the interactions is going to be Higgs particles. So we have to be clever about what we trigger on. And the challenge is to separate background from signal. So what we do in our experiments with the trigger, we reject 99.99998% of all the events immediately. We save the rest. This is about 10 terabytes of data per day, 1 petabyte per year. It's not horrible. We have thousands of computers around the world that are doing this. We have about 25 petabytes at CU Boulder in our computer center. But we use worldwide computers to do this. So this is actually data. On the right is my experiment CMS. On the left is the competitor. So this is looking at a Higgs particle going to 2 photons. And you can see there was a bump here. And there was a bump there at the top. And this is subtracting off the fit from the data. It was sort of a smooth background. The experiments plotted it in a different way, but they found Higgs to gamma gamma in exactly the same spot, around 125 GeV. I don't think this would have been compelling enough to say that we found anything. But we also look for Higgs into ZZ. The Z can go to 2 muons. So what you see here in red is a bump in 4 leptons. And the same thing in Atlas right here. So now we have 2 channels and at the same mass as the 2 photon channel. 2 photon channel, 4 lepton channel. So it was starting to get interesting. Now the question is, could we claim that something was new or not? And this gets down to, we also look for Higgs into WW. But the W decays to an lepton and a neutrino. Because you're missing neutrinos, you can't get a mass right at 125 GeV. They go right through the detector. So we got some smear here, some excess that we could attribute to something. But again, it doesn't help much to the significance. And as we'll build that up with more and more data. But there was sort of a third channel where it looked like we might be seeing something. So now we can say, okay, there's something there. And the standard in our field is 5 standard deviations to say that you have something. So, what's the chance that the background could fluctuate to 3 times 10 to the minus 7th in probability? To give you an idea, I think it's sort of a cute argument, is you ask, how often would you have to flip a coin in order to convince yourself that there was something wrong with the coin? So let's say the coin was defective, or maybe it was just the one you wanted. They came up heads most of the time. So you started flipping it. And you can't say much the first time. We know that's 50%. The second time doesn't help much either. You'd have to get 22 tosses all coming up heads before you would say, okay, there's something wrong with this coin. I'm sure people would conclude that beforehand, but that's our standard in our field. So then the question is, does the Higgs boson evidence reach this in individual experiments? And it turns out this is what's this showing you in terms of probability. As we move this way, this is a probability that the background could fluctuate to that point, given the data. And we find that both experiments, CMS on the left, Atlas on the right, had a probability of more than 5 standard deviations, adding together those 2 channels. The dimuon channel was about 3.5 standard deviations, and the muons was a little bit less. But together, plus adding in some other channels, got you above 5 standard deviations. So we discovered a new particle. And the mass, compared to what you expect theoretically, there's right here, this green line is what you would expect with a standard model Higgs. And right at 125 GeV or 126, we're getting a prediction that theory says we should find in terms of production. So these things look pretty good. So we thought the Higgs boson might exist. Some people thought this back in the 60s. And we knew how often it was produced and what it should leave in the detector. And we found something that looks just like that. So does that mean we can claim that we saw the Higgs boson? An example might be of why we didn't do this is when Columbus went to the New World, if they had had newspaper articles back there in 1492, he might have shown we discovered India. That's probably what he would have said, because that's what he thought he found. So we think we found the Higgs boson, but we were very cautious in our 2 publications from the 2 experiments. The CMS says observation of a new boson. We know it's a boson because it couples to 2 photons, so it had to be spin 0 or spin 2. But we didn't call it a Higgs, and it turns out the Atlas collaboration didn't either. So how can we say that we found the Higgs particle? Well, we just need more data. I know that's what scientists always say. Just give me more money and let me run longer, and I'll prove it to you. But these are plots of different things. Signal strength, the probability for these things happening versus theory, and the best fit for these 3 channels compared to sort of standard model Higgs. And you can see they all sort of agree, but they're off to one side or not. So with more data, all these points should lie right on the green curve. If they lie off, it probably means that there's something else. Like there could be charged Higgs or 2 Higgs or Higgs doublet or something like that. So what we need is just more data to measure these cross sections. After we come back at higher energy, we think we'll get about 20 times the data. So we should be able to see whether these points lie on the green curve. So there are problems with the whole Higgs model, which one of the questions is, how can a mass be only 125 GeV? People would like to have it be even heavier. And it turns out that there's something called a fine-tuning problem where there has to be some cancellations, again, from scattering of Higgs particles on Higgs particles that get it down to 125 GeV. So it could be that there's some new physics that would come in that could explain why the Higgs boson is so light. And that sort of broad brush of that theory is called supersymmetry. I'm not going to talk about supersymmetry, but it's for every particle-like object, you have a supersymmetric particle. And it was made in such a way that it cancels all the loops that come in scattering so that you end up getting a light mass. Okay, so again, this came out of electroweak symmetry breaking. This was, the Higgs particle was designed to say why the weak nuclear force and electricity and magnetism were basically the same type force, or same type object. The experiments we think will continue for decades. There are plans to go through 2030 with increases in energy and collision. It puts a tremendous pressure on experimenters to find the right detector. Silicon won't work, you know, five years from now. And our group is now working on diamond detectors, sort of radiation-hard material. But there are other groups working on other radiation-hard material. There's also a talk of building an electron-positron collider. There was one planned at Fermilab that would go beyond the site boundary at Fermilab. But again, people didn't want an accelerator near their property. They were worried about radiation. So it's not going to happen in the US. It could happen in Japan, could happen in Europe. I think we've discovered a new particle at 125 GeV. We need to know exactly how it decays to say that there's only one Higgs. There could be others. There are theories that predict this. And some of them use this to try to explain dark matter. You know that we think that the flat rotation curves around the center of the Milky Way come about because of dark matter. And if some of the supersymmetric particles don't interact strongly with normal matter, so they could be the dark matter objects. So I think it's an exciting era, and stay tuned. Yes?
With the higher energies available in cosmic rays, is there anything that we can learn by observing cosmic ray interactions?
So the question is, there are higher energy cosmic rays, and there was supposed to be a site, a northern site, near here in southern Colorado. The difficulty is to be able to instrument, you know, close to where things happen. I would say I would probably duck the question in that I tend to think that a lot of what's gone on with cosmic rays in the southern hemisphere at Auger have done things like found tau interactions, but I don't think, unless we come up with newer ideas on how to do newer instruments besides scintillation light or shrink-off light from the atmosphere, I don't think we can compete with accelerators. I do think there's a real need to put a cosmic ray detector in the northern hemisphere so we can see the whole sky. But I don't know if it can address things like this. It has to be a very unusual object that travels a very long distance and then decays. And I think we just don't have good enough instruments to have the accuracy. That's my read. It's pretty far afield from what I do.
Even though we have orders of magnitude.
You get much higher energies, and but you have to be careful. When you talk about much higher energies, the incoming particle has much higher energy, but the particle it's hitting is at rest. So it is higher, but it isn't a billion times higher. Yes?
What are you going to be looking for with higher energy accelerator that you're
Oh, so the main goal will probably be to, maybe I have, I turned this off. So some of the things that are beyond the Higgs, the big thing is supersymmetry. So for every electron, there's a supersymmetric electron. For all the fundamental particles, there'll be supersymmetric particles. People are looking at gravitational effects. We've not been able to see gravitational effects in accelerators. People would like to. String theory is, it was very fashionable in the 90s. And many universities hired a string theorist. But most of the results for string theory were at too high an energy. So I think some of the brightest people are doing this theory, but it has little impact on the experiment yet. But so we're trying to find some evidence for string theory to know whether we're in the right direction or not. There's things about extra dimensions that show up in terms of sort of streams of particle in one particular area or another. But I would say the meat and potatoes, if you like, is going to be really pinning down the Higgs. This is what we have now. And we have just one, or we have two. But one of the exciting things about running an accelerator like this, you're at the energy frontier. So it could be you hit a threshold and something interesting happens. That's what's happened at most of the other accelerators so far.
Is there any chance that with the higher energy, you'll also get a higher flux?
Oh, the higher flux comes with one's ability to squeeze the beams down.
Have stronger magnetic fields, right?
We can't go to higher magnetic fields. The magnetic fields, we're not quite running at 8.36. We're running at 4/7 of that now. So we can go to that field. It's just that people sort of got chicken with the superconducting problem. They didn't want to go up close to it. So when the magnet quenches, it has to dump a lot of energy. And they end up going into huge, they have to go through wires and then into huge steel blocks on the side of the tunnel. If they go through the magnet or they go through a vacuum chamber or something, they go right through. I mean, the beam can vaporize a block of copper. So I forgot exactly what you asked now.
You have more flux, you got more.
Yeah, so flux is not, the flux, the biggest problem with the flux, I think the accelerator can handle it. The problem is with detectors. So we have a soda straw like this. We start to have 50 interactions in there. So we have lots and lots of interactions, and we call it pile-up. And so you have to know how to associate particles to those. So you end up having more background. It's harder to ferret out good events.
Also, is supersymmetric particles different than antimatter?
Yeah. So antimatter is regular matter. That's wrong. So for a proton, there's an antiproton. So when I drew this picture of up, up, down, an antiproton would be U bar, U bar, D bar. So they're just made up of anti-quarks. Supersymmetric particle is something totally different. And these things are not fundamental. Protons and neutrons are not fundamental because they're composed of something. An electron or an up quark is fundamental in that we don't think it has any physical extent. It's not composed of anything else. So the supersymmetric particles are meant to be are related to the fundamental particles. And I was trying to say this when we talk about mass and the Higgs particle coupling to these objects. The Higgs particle couples to these quarks. But in a proton and a neutron, we know that these move around near the speed of light. So it's the kinetic energy from these quarks moving inside a proton or a neutron that give you a mass of around 1 GeV, 938 MeV over c² for a proton. it's due to the kinetic energy. It's not due to the fundamental mass of the quarks. Yes?
So the belief that the fundamental particles have no physical extent, is that come from just the failure to measure it, or is that predicted by?
You could say we're not good enough. Yeah, I think it's I mean, people have, sometimes it's described as peeling back layers of onion. So, you know, eventually you can't peel back anything else, so you say, okay, this is it. But you're absolutely right. I was talking with Stephen earlier about the experiments to look at the electron dipole moment. So if an electron has some distributed charge, it's not fundamental. But so far there are only limits. And so at the moment we say it's fundamental. And string theory would say these are stringed objects that are vibrating, so you're never going to see, you know, any physical extent to those. The other thing you can do, by the way, with point like, you can scatter these against each other like electrons on electrons. We can scatter and see if the point like cross sections that we calculate are, you know, just continue at the high energy. And that's been done at Stanford, and it's been done at in Japan, and it's been done at in Europe. And so far we'd say the electron is point-like, but it's only good to a certain degree of measurement accuracy. Yes?
I don't know the answer to this. Do quarks, when they're within a nucleus, do they interact, say, like proton and neutron, or do they stay independent? They stay in their own...
So that's a great question, and it turns out that we tend to think of them as like a soup. You know, you can have Campbell's up and Campbell's down. You know, they're all together. When you have other protons, we know that proton in a nucleus, there are gluons that hold the protons together, protons and neutrons. We know they remain separate. And it's interesting that these are pretty old experiments, but they're experiments that were done shooting neutrons on carbon. So carbon-12 is 6 protons, 6 neutrons. And so if you rearrange those, you can make 3 alpha particles. And it turns out that if you hit the right energy, the carbon-12 tends to break up into 3 alpha particles. So I don't quite know the answer, but I would say that the binding, if you like, for a proton-neutron is strong enough so that they stay separate from other protons and neutrons. And in some nuclei, like carbon, for instance, you may have alphas there a good portion of the time, 3 alphas floating around. It's not my level of expertise. It's called a selectron for S electron. What?
Supersymmetric. Yeah.
Oh, where did it come from?
No, I mean, how do you describe it? Whether it's proper.
Well, so it's done with it's meant to be symmetry and spin statistics. So for every fermion, like an electron, spin 1/2 object, there would be a supersymmetric boson, a partner. And it was done that way so when you look at scattering cross sections, and you tend to have things that can be loops of quarks that can run around, and they give you one sign in terms of the scattering cross section, and bosons give you the opposite sign if they're in the loop. So if you can create, if you have, for every electron you have a supersymmetric electron, it provides a natural way for the loops to cancel out and to give you sort of a finite cross section. I don't know if that helps you, but I mean it was a theoretical idea that was designed to, like the Higgs field, by the way, to say why are these things so light? Because without something else, then again now these cross sections diverge. So we know that this isn't the final word. There has to be something else that's everywhere. Anything else? Yes.
So just to clarify, so this Higgs field is what explains why.
Fifth.
Pardon?
Fifth field.
It's the fifth field.
Yeah.
And that's what's saying why, when at further distances, the EM force is different than the weak force.
Yeah. So the idea is that you have one force that with different carriers. That's why I started by saying I don't really believe in action of distance. Something is exchanged. Okay. And so in the weak nuclear force, the force carriers are the W and the Z bosons that are 80 times more massive than a proton. So they're very heavy. And so it's the drag of these force carriers through the Higgs field that cuts off or absorbs the weak nuclear force so it doesn't get outside of the nucleus. But the photon with massless can travel a long distance. Yep. Yes?
Can this so-called graviton be part of this project to be detected, or some symptoms, or to be connected with this Higgs boson?
Can the graviton be a Higgs boson? I don't think so. But it turns out
the symptoms of existing of this graviton.
I think of the graviton as something being exchanged. And I think of the Higgs field as something that pervades everywhere, pervades space everywhere. Sometimes it's described as, a constant temperature in a cold, dark cave. It's just uniform temperature. It's a uniform background throughout. Sort of like ether. It's something that's there everywhere. With the graviton, I think of it as something, I have a mass here and a mass there, and there's gravitons emitted between the two. And so when I start to pick up too many gravitons in my left fist here, then I know there's something else over here.
This project doesn't try to...
No, there are theoretical calculations predicting what the graviton would be. We haven't found the graviton yet. There's a large project in Washington and in Livingston, Louisiana. There's an experiment called LIGO, Large Interferometric Gravitational Observatory, something like that. And these experiments hope to see gravitational radiation. And but I don't know if they're going to see gravitons or not. The best idea is that the force carrier, the graviton, is a spin 2 object. But there is no quantum field theory for gravity, which is kind of interesting. It's the one that we know the best, but so far it's avoided quantization like the others. So what we do, the same as with the Higgs, is we take different theoretical predictions for what gravity might be. Again, you have to say, okay, how is gravity going to interact with this object? And you say, can we find any signature in our experiment that might say there's a graviton? And we've definitely looked for things, but we've got nothing to report. I mean, personally, well, it might sound like science fiction, but I'm not sure the graviton is even, it might be a tachyon. It might be something that's different than the other force carriers. A tachyon is something that can move faster than the speed of light, and we had an embarrassment last year with the neutrino. But I'm not. The best theory of the astrophysics model has dark energy and dark matter. We haven't seen those in the lab, so I'm not a real... I want to look for alternative descriptions. You know, if we see something, then I completely change my mind. But I think if we can't find those things, then, you know, I prefer to say gravity is different at long distance, for example. That's my preference. It's not the standard model. It's pretty far away from the standard model.
When you think of gravitons, how do you try to reconcile them?
Well, so with Einstein, with GR, Einstein GR, it doesn't work. Absolutely doesn't work. But I would point out that there was another model that's been sort of passed over by Schwinger. He used something called source theory that was explaining things like the lensing, things like that, that agreed with Einstein, but with a rather different interpretation. And I mean, I don't want to claim anything. I'm just saying, you know, personally, I'm like a guy from Missouri. Show me. You know, I want to see something in the lab before I sort of buy into this theory. And you know, just calling something dark matter and dark energy sort of means that we don't understand it. Okay.
Well, let's think of, oh, sorry, you have a question?
No.
No,
No, I was just wondering, is classical tunneling out of a nucleus,
for alpha decay.
is that mainly electro-Coulomb interaction still, or is it electro-weak?
No, we use just a Coulomb interaction. Actually, my institution, that's the George Gamow, came up with that. You know, the tunneling through. There are these Gamow-Teller rules for.
The reason I asked, because you said they were about equal, but it's still not on the size scale of the boundary.
That's a great question. So, I said at 10 to the minus 18th. The forces were the same, but what's the size of the nucleus?
10 to 9
Yeah, so it's 3 orders of magnitude different.
More than 30.
Yeah, exactly.
well, I guess we'll just thank our speaker again.
Okay. Thank you.